what's on the end in a moment. There's two different types of polymer that we're going to have to classify based on how they're made. And then the way they look when they're formed, you can tell which is which. There are condensation polymers. We'll talk about that. And then addition polymers too. Before taking this class, I doubt if you've ever heard the term ester before as a type of compound. But I know that everybody has heard of a polyester, haven't you? Polyester. Yeah, you can take esters and string them together to make a polymer. And it's good for fabrics. You know where else polyesters are used? Carpets. Carpets are mostly polyester. Yeah. Do you think they're the same polyester, what we wear and what's in the carpet? No. Molecules that are polymers don't have to all be the same. We'll talk about how properties can change. Yeah?
So where's polyester found on Earth?
You have to make it. It's not naturally occurring. There are some polymers that are naturally occurring. Proteins are an example. Proteins are polymers that your body makes. And we don't have to try to make them or make them outside of our body and then stick them in. And we just make them. All plants are made of cellulose. Cellulose is just a whole bunch of repeating sugars. So cellulose is a polymer too. Yep, among others. Okay, so we're going to start with condensation polymer. We'll start with the polyesters. You know what? I'm going to not show you that structure yet. I just want you to see this. My structure, I don't know, it's a little bit obnoxious, and I want to go a little bit simpler first.
Why is it called polyethylene if it only has single bonds?
That's a great question. Ethylene is carbon double bonded to another carbon. We call it polyethylene because it started as ethylene. And the double bond became a single bond when the polymer was made. I'm going to go through all that with you. So that will be answered. See this compound? How many functional groups are on it? There's two. There's one on this end and there's one on that end. We would call this compound a diacid. It's got two acid groups on it. You with me? Diacid. Reach first. This compound in green would be a diol. It's got an alcohol there and an alcohol there, so we would call that a diol. That's what I'm talking about. Now, these two compounds, they can form a bond. They can have a condensation reaction occur, and this part of the molecule, of each molecule, get removed to make the water, right? And so these two molecules can join together and condense into one bigger compound. But when that one bigger compound gets made, the end of this compound still can have a reaction occurring there, can't it? This is an alcohol group over here. The end of this molecule, this is an acid. So if, now I'd make the acid in red. When these two come together, molecule 1 with molecule 2, then over here is molecule 3, and now 1 and 2 have become 1. You want to get that? Molecule 3 can come along, and the acid part of this can join up with the other side of the alcohol. See that? So we can have a molecule that's got 3 molecules joined together. Are you seeing what's happening here? We have an acid group and an alcohol. The other end of this alcohol molecule has another alcohol side to it. So that alcohol side can find the acid of another molecule. And a chain can be made. And then the other side of this acid can join up with another alcohol. And that's how polymers can be made. If you have two active sides that can both form reactions and cause molecules to join together, then you can get these long, huge polymer molecules. Now, I covered these up. The ones that I chose, I don't know why. I wasn't trying to be obnoxious with these, but I think it turned out that way. Where I've got 3 carbons between my acid groups, over there I just put 1. And I've got 2 carbons. I guess I had the same thing over there. So this is going to show you several repeating units, and it's kind of long. I don't know if you want to write it down. You don't have to. Oh gosh, that's long.
Would that be the same thing as that, just like longer?
Yeah, it's the exact same thing. Yep. Really, all we're interested in is seeing is this. That thing right there. That's an ester connection. Then, not too far down the line, there's an ester connection. Oh look, here's another ester connection. So these esters keep being made with alternating, and I was using the coloring so that you would see, here's my diacid, and there's my dialcohol. Diacid, dialcohol, and they just keep alternating. And this becomes a long, giant molecule. And how long can this thing get? Is there a certain number that it'll just get tired at? No. You keep making these until you run out of one of the monomers. Monomer, like these would be your monomer. That's what you start with. I don't know if these are distracting to you. There's another product of this reaction. What's the other product? Water. How much water? Not just one molecule?
Continuous.
There was a molecule of water that was made when this connection was made, right? And then another water molecule for that, and another water molecule for that. So, yes, one for every link, water molecule comes out. Now, there's been a lot of chemistry that we've talked about for the last several days. I'm more interested right now in you knowing what the organic things look like. We're not too interested in the water. I'd like you to know that there is water made, but don't freak out, if you forget to put the water, because if you can get the organic things right, I'm pretty happy. All right. So the properties of polyester molecules will depend on how long these starting compounds are. Like you might have 10 carbons in a row between the acids, and then you might have 6 carbons in a row between the OHs. These lengths of what we call the monomers, they'll determine what the properties are. That's why I say the polyester that you wear in your clothes is probably not the same as the polyester that we use in rugs and carpet. Anybody have any questions about that? Go ahead.
So how many water molecules, like exact number, for that example?
I'm going to count this as an ester connection, and the one at the end as an ester connection. 1, 2, 3, 4, 5 waters.
All right, thank you.
Okay. Anything else? You done writing? That was long. Gosh,
So there's a-
I'm sorry to do that to you. What's that?
There's a water molecule for every ester.
Yes. Yep. Polyamides are the exact same connection as polyesters, except you've got a C double bond O connecting to an N rather than an O. Everything else is the same. So you're going to have a diacid, just like we did for the polyesters. But then this thing would be called a diamine, because the NH2 is called an amine group. So yeah, we've got an amine on one side and an amine on the other side. So would you be able to write what the product would look like if I told you that it was the same thing as a normal amide connection, just on both sides of the molecule? And it's just like a polyester, except for it's nitrogen instead of oxygen that's making the connection. That is going to be what you would expect. Here's our diacid, and we lose the OH off the acid and the H off of the N, and we make that connection. So that's an amide connection, but then there's one over here too, and then one over there. Again, 5 amides made, counting the ones on the ends. I don't know if you want to write all this down. That takes so long, and well, I'll leave it. If you do write it down, I do recommend using something to color these. If you have a highlighter or something, just highlight the diacid or highlight one or the other, or use 2 different colors. I think that helps you to track how those became that long thing. Of course, plus water, plus n number of waters, n being equal to how many links were made. Yes, ma'am?
When you're writing this, could you ever end the quote thing wherever, like in between, one of the...
Like right there? Could you
Yeah.
end the parentheses right there? Yeah, you could, as long as you had 2 full repeating units. You could.
Sorry, space.
Yeah, that's fine. That's fine. All right. Now, what other polyamides do we know of? I just told you amides were peptide links, so that proteins are polyamides. But in non-living things, one of our most well-known, probably our most well-known polyamide is this thing right here, nylon. Nylon is it's a plastic material that's it's a polyamide. It's made this way.
So, wait, is that nylon?
Yes, it is. The lab that we do on Monday, you're going to really enjoy it. It's one of the coolest things you'll ever see in a chemistry lab. I never get tired of it. Every year I just really look forward to doing the nylon lab. You're going to have a diacid. It's actually not quite a diacid. I'll talk about it on Monday what it is. It has CLs on the end rather than OHs, but it behaves the same way. It's called carboxyl chloride. It's got 10 carbons and then these functional groups on the end. So it's a real long thing. And the 10 carbons cause it to be almost completely nonpolar. And being nonpolar, it won't dissolve in water. So we're going to wind up dissolving it in a nonpolar solvent, cyclohexane.